Welcome to Activity 5.2. Our learning target for today is we're going to investigate what happens at different plate boundaries and why. So the expectations for you is that you're going to make observations and discuss with your group the actions that occur at plate boundaries. I will record my answers in my book on pages 42 through 44. So that's where you're going to record them. So it's not me recording them, it's you recording them. Now, I don't mind if you work with groups, but you have to work. Some of you are going to be restricted because you're behind with your work, and some of you are going to be restricted because you just don't work very hard and you're doing a lot more talking than work. So make sure you're doing what you're supposed to be doing. Make sure you're working hard. Groups should be small groups. You don't need to get 5, 6, 7 people in a group, but you all need to be at the same spot. Likewise, you can also work alone if you want. So let's turn to page 42. Here are two towels. If I slid these two towels together, so I put my hand on both and I pushed them towards each other, this is what happened. So what are your observations? When I move these towels together, what do you see? What's happening with each one? So go ahead, pause the video and record your observations, then we'll talk about what happened. Again, just like in Activity 5.1, you need to answer the questions before you move on to the answers. That is the expectations. It's far too easy just to move on and copy stuff down, but that's not how learning happens, and that's not how an individualized unit works. If you do get caught doing this, or if you get caught copying someone else's, you will be in the penalty box. So go ahead, pause the video and answer this question. So what did you come up with? Well, did you notice that when the towel plates moved towards each other, they crumpled up? And this would be the simulation of how folded mountains are created. So compare this simulation to the formation of mountains. So go ahead, pause the video, in just a sentence, how do you think they compare? All right, so you've had a chance to look at the simulation and think about how they form in the real world. Well, mountains form when two continents collide and neither one moves underneath the other. So when you look at these two towels, neither one slid underneath the other. They crumpled up and they formed some large mountain chains, such as the Himalayan mountains. So when plates move towards each other, why do you think one plate sometimes slides underneath the other? Well, sometimes they do not move in this way. So go ahead, pause the video and answer this question. All right, so what did you come up with? Well, one plate may slide underneath another plate because it's thinner and denser. And we've been talking about this quite a bit in this unit, so this should have been a really easy question. Now, if it's two continental plates, they tend to crumple up. But if it's an oceanic plate and a continental plate, the thinner one, which an oceanic crust is thinner, so the lithosphere is going to be thinner, and it's more dense, it's going to slip and slide underneath the continental plates. Now, when two oceanic plates come together, you tend to get some deeper trenches. You have lots of subduction. You have a large subduction zone, and it's going to get a really deep trench. But one will ultimately slip underneath the other one or slide underneath the other one. So what would happen if we changed it up a little bit? Instead of having two towels, I used a notebook and a towel. What do you think is going to happen? Well, you can see what happens here. So can you describe the two types of convergence that you see here? We already talked about this one, but what's happening here? So hopefully you see that in one type, the plate simply slides underneath the other plate. This is where your subduction zone is happening. This notebook would symbolize an oceanic plate that's thinner and more dense. And a towel would represent or symbolize a continental crust. It's going to be less dense, it's granitic in nature versus basaltic in nature, and it's usually the one that's going to stay on top. Well, it is if it comes in contact with an oceanic. But when this happens, you're going to get folded mountains, but a lot of times, eventually one of the plates will lose out and it will disappear eventually. So why do you think that sometimes plates slide underneath other plates and sometimes they do not? So I don't have an answer for that, but what are your thoughts? Are you thinking density has something to do with it? And if you are, you're exactly right. So how about this question? What would the Earth look like if there was no water on its surface? And we kind of looked at this when we looked at the Mid-Atlantic Ridge. What do we notice running right down the middle of the Atlantic Ocean? The Mid-Atlantic Ridge. We got mountain chains. We've got lots of things happening underneath the water that is also happening on the land. So geologists for the longest time thought that the oceans were, flat, it was sandy, kind of like by the beach. And you would walk on one side of the ocean and it would just keep going down and eventually come up on the other side of the ocean. But that's not what scientists found. They found that the ocean floor is made up of rock. So, and Earth without water would look like a rocky surface. It would have mountains, it would have valleys, it would have volcanoes, just like we see on land. So these are some of the key points that we need to understand after going through this activity. And some of these are going to be on the activity 5.2, check for understanding. So there's a lot of relief on the Earth's surface, whether you're under the oceans or whether you're on land. And there's two major average elevations, the elevation of the continents and the elevation of the ocean floors. Now, oceanic plate material refers to plates that have oceanic rock on the top edges of the plates. Oceanic plate material is relatively thin. That's going to be more dense. Continental plates material refers to plates that have continental rock on the top edges of the plates. Continental plate material is relatively thick, and it's going to be less dense than oceanic plate. And water, when we look at water, water collects in the oceans because it has a lower elevation compared to the continental landmass. Water always flows downhill to reach the lowest spots. So your oceans are going to be the low spots on our planet. Now, when we look at the major rock types, I've referred to this off and on throughout this entire unit. A lot of times when I talked about continental rock, I talked about it being granitic. And one of the rock types is granite. It tends to be thicker, it tends to be less dense. And you can see the densities here, 2.65 grams per milliliter. And a lot of times when I talked about oceanic crust, I talked about it being basaltic. It's going to be thinner, but it's going to be more dense. And so when we talk about granitic rock, basaltic rock, it doesn't mean the continent is entirely made up of granite, but it's a rock type. Now, our understanding of the Earth's surface became slightly more complex as scientists realized that the rocks that make up the ocean floor is different than the rocks that make up the continental land masses. The main difference is that the rocks of the ocean floor are not only thinner, but they're also denser. And the rocks of the continental land masses are both thicker and less dense. So what does all this mean? Well, we know that when edges of two plates are both made of lesser dense and thicker rock material, in other words, continents tend to stay on the top and the edges of the plates. So let me go through that again. So when the edges of two plates are both made of the lesser dense and thicker rock materials, so we have the continents on tops and edges of the plates, neither one will move into the interior. They tend to crumple up. It's not until you get the more dense material, such as the basaltic rock, the oceanic crust, where you're going to have one subducting underneath the other. So therefore, they both stay at the surface and they crumple if they're both going to be your less dense, thicker granitic type rock. Now, the ocean floor is a little bit different. As a plate with ocean floor rock material on the top edge subducts beneath another plate, it becomes even denser. And the reason why it becomes even denser, as it subducts underneath the plate, a lot of the less dense material will melt first and it will rise to the surface, and a lot of times it will create new land, such as what we see in the Andes Mountains. So this makes it sink in farther and it pulls the rest of the plate behind it. So make sure as you're going through this, if you have any questions, ask. This is a lot, and we're covering a lot of material with you. And by the time you're done with this, you're going to be a little, mini geologist. You should be able to explain a lot of what's happening inside the Earth and on the surface of the Earth as plates interact. So let's go on and let's look at page 43. What I want you to do is I want you to think about all these terms that you see down here in these arrows. Where would you put them in? So what I want you to do is do this with a pencil, so if you're wrong, you can check your answers. Again, I want you to fill this in first, then check your answers and erase if you need to. It'd be very tempting to go on to the next slide, which is where the answers are, but yet it's very wrong. So go ahead, pause the video and label everything. All right, so you've had a chance to label everything. So let's start to look at these. Where would we put things? Well, we know where the ocean is. We know where there's magma. How about volcano? We can see a volcano, so a lot of these are pretty easy for us to label. We know where the ocean floor plate is. It's right here. And I'm going to put it right here because here's your oceanic crust and here's the top part of the mantle, and combined that makes the lithosphere. Continental plate, I'm just going to put right here, and it's both of these. It's all the continental crust in the very, very top part of the mantle. So we know that this is going to be moving this way. This plate, I'm actually going to slide around like that, and it's going to be going this way. You might say, well, where's this one going? I'm actually going to move this, and I'm going to put it here. So where do you have your less dense rock? So this is going to be your less dense rock, remember. This is the continental rock, or the continental crust. This is your granitic rock. And here's going to be your more dense rock. Where's your very hot rock? Well, I could see you putting this in a couple different spots. You can have it down here. It's going to be hot. You can have it right here because it's starting to melt. So you can have this very hot rock in a couple different spots. So when we look at the answer key, it's here. You could have had it over here. I can understand if you put it right here because this rock is melting. So of course it's going to be very hot. So did you notice how we did? They put the ocean floor plate here. I like it better down here. But we got everything correct. And a really good example of this where an oceanic plate is subducting underneath a continental plate are the Andes Mountains. And again, this less dense material that melts first is going to come up here and form volcanic mountains. You tend to get volcanoes when you have subduction zones, an oceanic plate going underneath a continental plate. But if it was two continental plates, and that's what we're going to take a look at next, you don't get volcanoes, you get folded mountains. And even here you can see that one plate eventually subducts underneath the other. It just doesn't happen very quickly. So go ahead and look at this one. It says, what's wrong with this picture? And what I mean by that is it's not going to subduct this quickly. Eventually it will, but I don't want you to get the idea when two continental plates come together, one's simply going to slide underneath the other one. Right here and here, this would all be crumpled up, and it would be more like two cars hitting each other head on, and one car, both the front ends are going to crumple upward. So you should have a lot more crumpling here, and I can understand there would be eventually one plate going underneath, but this kind of makes it look like it's just slipping right underneath very easily, which it doesn't. So go ahead and label all the parts, and please do this before we go through the answer. So go ahead, pause the video, and label everything. All right, so you've had a chance to label everything. And again, most of this is pretty common sense. You have your continents, you have your continent. You have this ocean, or this plate moving this way, this plate moving this way. You can have your very hot rock down here. You have, this is less dense rock. This is less dense rock because it's both continental, it's both granitic. You've got your mountain range here. You've got your crumpling. I would say happening right here where they come together. And again, I would have put more crumpling over here too. Otherwise, it makes it look like this plate is just simply subducting underneath, and that's not quite accurate. So how did you do with labeling everything? You've been working with IXL, and hopefully this is becoming pretty easy for you. So let's move on. Here's the answer key, and you can see that we got everything correct. So let's move on to the making sense questions on page 44. So I'm going to link this video, so make sure you watch this video as you're moving through. So go ahead, pause the video, find this video, When the Earth Erupts, Subduction Zone, watch it, come back, and finish the making sense question. So go ahead, pause the video. All right, so you've had a chance to watch the video. So let's go through the making sense questions. Explain why ocean floor plates subduct beneath continental plates. Go ahead, pause the video, answer that. You should be able to answer this by this time. If you have no clue, you need to back up and you need to do the last couple lessons again because you're not paying attention. You're not learning what you're supposed to be learning. So go ahead, pause the video and answer this. Otherwise, go back to 5.1 and redo it. All right, so you've had a chance. Explain why ocean floor plates subduct underneath the other one. Well, remember, the ocean floor plates subduct underneath the continental plates because they're thinner, they're denser, so they sink relative to the thicker and less dense continental plates. So again, the more dense plate's going to subduct underneath the less dense plate. We've been talking about that over and over and over because it's an important concept when it comes to plate tectonics. Now, once the slab moves beneath the other surface, gravity tends to pull it as well. And that's where you get the slab pull part of the ridge push slab pull theory. So once it goes underneath, it's actually going to be pulling the rest of the plate with it. Along with the convection currents, it's going to keep those plates moving. So let's look at the last making sense question. At this point, how would you answer the driving question? How is the Earth changing? And so go ahead, put a couple sentences down. So go ahead, pause the video. How did you do with this? Can you answer this? Again, I'm going to be honest with you. If you can't answer this, if you do not know how the Earth is changing, you need to go back to 5.1 and redo 5.1. You need to watch all the videos, and you need to redo 5.2. So it's kind of a rhetorical question. There's no one answer. You can have lots of different answers. You can talk about how the plates are forming mountains and volcanic islands and how the plates are slipping past one another, and some plates are going underneath one another and forming trenches and subduction zones and island arcs. And when two continental plates come together, they're forming these folded mountains, these huge mountain ranges such as the Himalayas. So those are all good examples. Now, do the different types of plate movements lead to other features and events on the Earth's surface? That's what we're going to start to explore next. Now, the last thing I want you to do before we move on is we're going to add a couple scientific principles. So, wrapping up this lesson, the solid material in the Earth's mantle moves by convection. Now, the movement of the mantle acts like a conveyor belt as the plates slide around on top of this layer. Plate boundaries are aligned to places of geological activity, such as earthquakes and volcanoes. In fact, that's how geologists figured out where the plate boundaries are. There aren't signs that say, hey, here's a plate boundary. Scientists found out that there's all these earthquakes and all these volcanoes, and they tend to be aligned with the plate boundaries. So the plate boundaries were found as a result of these earthquakes and volcanoes. Now, the different features on the Earth are a result of the two different types of plates that exist on the Earth, continental plates and oceanic plates, so which have different densities and thicknesses. So one of the things I want you to do is take a look at this video, Convection Currents and Plate Boundaries video notes. So I'm going to click on it once.
All right, so
here
the driving force behind plate tectonics.
You can start to see it. You can only see part of the screen. It's about a 2-minute and 21 or 27-second video. So take a look at it. It'll go a little bit more in depth with convection. So it's not a very long one. So I will link this video up. Make sure you watch it. So go ahead, pause the video and watch this. So the very last thing we're going to do is we're going to add some scientific principles. Number 5, plates move on the Earth's surface in a variety of ways, including towards each other, away from each other, and alongside each other. When two plates interact, the geological features and events common on Earth occur. This is how we get volcanoes. This is how we get mountains. This is how we get trenches. This is how we get earthquakes. So a lot of these natural phenomena that we see are a result of the plates interacting with each other. And then 7, there are two kinds of plates. There's oceanic plates. These are your denser plates. These are your thinner plates. These are primarily basaltic type plates. And then you have your continental plates. They're going to be thicker. They're going to be less dense. And it's got more of a granitic material in it, or it's composed of more of a granitic material. So make sure once you finish this video, you complete the checkup or check for understanding on this. If you do not complete the check for understanding, you will have to do the alternative assignment that goes along with it. So slow down, use your book, find all the answers in the check for understanding so you can pass it the first time and you do not have to do the alternative assignment.